This is the 7th video of the BattleZips-Noir series, and in this video we're going to look at writing tests for Noir proofs. In the process, we're also going to be exploring the Aztec Typescript libraries and show how they are important for the testing process, and also interacting with Noir proofs in general in TypeScript. Let's go ahead and get started. So looking at the repository, we have two files we test in. We have a circuit.typescript file, and this is just for testing the validity of the board and the shot circuits. And then we also have a game.typescript file, and this is for playing an entire battleship game on chain and just testing that the verifier contracts work correctly. But we'll start by looking at the circuit.typescript file. So starting off, the most used TypeScript package out of any of them for testing, at least in this case, is going to be the Berettenberg library. And with Berettenberg, you can create proofs in TypeScript, set up provers and verifiers in TypeScript, and verify proofs in TypeScript. It also offers a whole host of other helpful functions. In this case, we are going to be using its Peterson hash implementation. But let's go ahead and jump into the test with that noted. So before we run any of the tests, we want to make sure we initialize a Berettenberg WebAssembly class. And we simply do that by importing Berettenberg WebAssembly and calling new on it. And then for most of the classes that the Berettenberg package provides, we have to supply the Berettenberg WebAssembly class into the constructor, like so here for the Peterson implementation. But for other examples, this is usually the case as well. You have to pass this in, and we'll see more of this in the front-end implementation in the next video. But going down to the tests, we first test the board circuit, and we want to ensure that all of the edge cases, the cases that should fail, are indeed failing. So real quick, before we jump into the board tests, we do a few more things here. So we actually get our board circuit by compiling the board circuit file. And as we can see here, we use a function called compile, and this is provided by the Noir WebAssembly package here. And this is really convenient because it allows us to compile directly from the Noir circuit itself. An alternative to this would be we would compile with Nargo, and to get the circuit in our TypeScript file, we would access that Acer file directly. But this is a bit cleaner and a preferable method personally. But once we have our circuit compiled, we grab the Acer for the circuit by calling that compiled circuit and accessing the circuit value from it. Once we have our Acer representation, we can then set up a prover and verifier with the function provided by Berettenberg. And likewise, like this, you just destructure an array and you have the prover and verifier in TypeScript. But moving down to the first test, we want to ensure that negative values are indeed failing for the circuit. This is expected behavior, but just for a complete coverage of the test, thought it would be important to include. So obviously this is going to fail because signed integers are not currently included in Noir. And moving on, something important to touch on is how Peterson hashes are created in the Noir files versus created in TypeScript. And this was actually tricky for a bit because when we were originally writing these tests, we weren't actually able to get the hash for the ship arrays generated in TypeScript to match the one computed in Noir. But the reason ended up being is because Noir treats numbers as 32-byte hex strings. So when we go here and when we make our Peterson hash for the ships in TypeScript, we can see here we are using a function called compress inputs. But to compress the inputs, we have to convert this ship array into an array of buffers that are converted from 32-byte hex strings. So here we have a function called num2hex, and this will just take in a number, convert it to a hex value, and based on the length of that hex value, we will add the padding necessary to result in a 32-byte hex string. Because again, when we create this hash with 32-byte hex strings, it's a very different value than just creating a hash from the numbers. We want to make sure it matches the format that is used in Noir. But once this is done, we have a buffer representing the Peterson hash, and in the next step in the ABI, we just specify this hash here. We prepend a 0x, and then we convert the buffer to a hex string. And then this is good to pass into our proof. Additionally, the array of ships, because remember the board circuit takes both the hash of the ships and the ships themselves as input through the ABI. And down here, we finally use those Brandenburg functions, create proof and verify proof. So to create a proof in TypeScript, what we need to pass into this create proof function is the prover we generated here in this before hook, the acer we have assigned here in this before hook as well from the compiled circuit, and finally the ABI we specify here. Something important to know about the ABI is the order actually doesn't matter for the inputs you specify. It might not seem that way with an object, but behind the scenes in this function, this is getting converted to a form where the sequence of these inputs matters. So I just want to make sure they're in the same order that matches the circuit, because that's another thing that could trip you up. But once we generate the proof, in order to verify a proof, we just use this verify proof function, and we pass in the verifier, again, that we generated up here in this before hook, and then pass in the proof that we generate on the line above. And this will return a Boolean value, verified. And if this were a proof where constraints were to fail, then obviously this would be correct and being false. But the fact that signed integers aren't even supported means it's just going to error out. So this expect will be the one that ends up being run. Moving down to some further tests, we want to ensure that non-binary z coordinates or z values are not accepted, because obviously there's two directions, horizontal and vertical. We want to ensure that any x values out of bound that is a bound above 9, since below 0 is just going to make the proof error. We want to make sure that constraints fail if the value is greater. We want to ensure that the ship is placed horizontally and its length exceeds the bounds of the board, that based on that initial, or the head of the ship where it's placed, it'll fail. Same with Y, we want to ensure that if a ship is placed low enough on the board that its length exceeds the rest of spots available, that it fails. And again, with Y, any value above 9 is going to be an automatic failure. Down here we test ship collisions, so we can see these first two ships have the same position. We expect this to fail. We expect it to fail when two vertical ships share the same positions. Just random ship placements where there's various collisions. And then finally, we just want to check that hash integrity is working properly. So if we supply an empty hash, it's obviously not going to match the hash of the ship array provided to the Noir circuit. And then likewise here with an incorrect hash. And then finally, we get to the part where we test valid placements. And now this takes us to the shot circuit. And for here, we don't need to go over all these steps again because it's pretty much the same. Obviously, instead of the board circuit, we are now compiling the shot circuit, so accessing the shot subdirectory. And first off, again, we want to test those failure cases. So we want to see if a shot will fail, if negative values provided. And again, this will just result in an error because negative values won't even be accepted as inputs to the proof. Here, out of bounds, any value above 9. Same for the Y value. And again, here we want to test hash integrity for the ships. So empty string is tested, an incorrect hash, but it's still 32 bytes. Then we're moving on to testing constraints related to hits. So for this first case, we're going to take a shot at coordinate 0, 0, where no ship is placed, but declare a hit. So the verification is going to return false in this case. And then for the next four cases, we're switching back and forth between Z being 0 and 1, and also declaring hit as a miss and miss as a hit, just to test that our ship placements are working correctly in relation to shots. And finally, we get to the valid shot section, and we have a few cases for this. But yeah, that does it for the circuit test file. Let's go ahead, check out the package.json real quick. We have a few helpful scripts for running tests. If we want to test the circuit file, we just do yarn or npm run test circuit. And then for the game, which we'll go over right after this, we do yarn test game or npm run test game. But let's go back to the circuit file and run the test real quick. All right, now all of our tests have passed. So that does it for the circuit test file. Now we can move on to the game. And the setup here is similar to the circuit test file. Let's go down to the before hook. Again, we want to initialize a Brandenburg WebAssembly class. We want to get the signers from our mnemonic that we provide in our env. So we'll name them Alice and Bob. And we have an initialize function here. So we want to pass in the Brandenburg WebAssembly class, and the second parameter would be a forwarder address, and we chose to use meta-transactions. Again, that functionality is built in, but we're not using it in this specific implementation. But let's hop into initialize real quick, and all this really is setting up our contracts. So we're deploying a shot verifier, a board verifier, again the forwarder, we're just going to use address 0, and then we're deploying the game. And as shown in the last video, when we create a new game contract, we want to pass in a forwarder address, a board verifier address, and a shot verifier address. That takes care of the contracts though, so the next step is initializing our Peterson hash function, and then creating a hash of the board for Alice and a hash for the board for Bob. And then we're going to pass these into the test file. Real quick, the boards and shots are just hard-coded up here. Okay, so going back to the test file, in the next step, we compile both the board and shot circuits and generate a prover and verifier for each of them. And once this step is done, we can then go and start a game. So we start off by creating an ABI for Alice's board, and then create a board proof for Alice. And again, the create proof function via Brandenburg library takes in a prover, an ASER converted circuit, and the ABI we specified up here. For the purposes of redundancy, we just verify the proof here, even though this will be done in the contracts as well. And then call the new game function for Alice and pass in her board hash and the proof to go along with the board. And if the proof passes successfully, then we can go to the next step, which is allowing Bob to join an existing game. And similarly, we create a board ABI for him, create a proof for his board, verify the proof here in the TypeScript file, and then finally join the game where we pass in his board hash and his board proof. We then confirm that both players are in the game, and once that is confirmed, we take the opening shot with Alice. We then go into this helper function called simulate turn, and this will play out the rest of the game for us. So the start of this function, we specify a shot ABI for Bob, and this is going to be taking the board for Bob, specifying if the previous shot was a hit, take the ships for Bob, and then finally get that shot from the Alice shot array imported from the other file. We then create a proof for this shot. Again, for the purposes of redundancy, verify in the TypeScript file, and then officially take the turn. And we go ahead and pass in true for the hit, pass in the returning buyer shot for Bob, and then pass in the proof that we generated up here. Repeat this for Alice, create a proof for the shot that Bob took previously, verify again, and then take the turn for Alice. And then we repeat this 32 times in total, and the game concludes with the Sinking of Bob ships in this last part. And here we just specify that last shot ABI for the shotproof. Complete this, and then finally game over. And the rest of the test file is just testing newer contract functionality that didn't exist prior to BattleZips-Noir from the old repo it was forked from. So we're not going to go over it in detail here, but we will go and run the test real quick. Great, so all of our tests have passed, and this concludes the video on testing Noir. The next video is going to mark a conclusion to the series. We're going to look at where our proofs integrate into a front-end application built in React. This is going to involve a walkthrough of how to set up a React app so that Node native packages are usable inside React Scripts 5. We're going to do a walkthrough of the React code and show where our Noir proofs are integrated. And then finally, we're going to demonstrate the importance of web workers and how they can be used to run the Aztec backend WebAssembly packages, which as of right now are required to run in a React app. But that's going to do it for this video. See you all in the conclusion.